Okay, perfect. Morning, everybody. I'm Bernhard from the University of Waikato. I'm going to talk about classifier chains this morning. I've just chosen this particular topic because there are too many different things, and so I've chosen one. And if you want to see some other things, there's a few of my students around who all have posters, and you can talk to them about that. Okay, so this slide is probably a little bit too small for you to read the details, and in a way, this morning Albert told us that we're too shy, so I decided not to be shy. But also here, this is a lesson for you in optimizing your H index or maximizing the number of your citations. So what you need to do is, you need to have a good PhD student first, Jesse Reed. Develop a simple method that's simple enough that people can read and understand it quite quickly, and that they then feel the need to improve on it, which means that they write a paper that has to cite you. But also, it should be a method that's reasonably robust, so it gets good results by itself, so it's actually being accepted for publication in the first place. And if you're lucky, it's been accepted as a method that others feel the need to compare to, even if they do something totally different. But again, they have to cite you if they compare you. So if you're lucky, then you get a conference publication with a couple of hundred citations. And then the next thing is you turn that into journal publication. And then people don't know which one to cite, and so like 50-50, some cite that, some cite that, and you get two publications with a couple of hundred citations, and your H index will never be more than 500, so it doesn't matter. That's split up between two publications. And then if you were really careful submitting your paper to a conference that gives you a test of time award 10 years after, because you got all these publications now, citations, when they look at it, they think, didn't give it like an award back then, but maybe we should have. And so they make up for that. 10 years later, you get a time of test award. And with that, what comes with that is that it's not listed here with a new journal publication summing up everything, and hopefully they will also get a few hundred citations. So your H index has gone up by 3 now with one good idea, which is cool. Okay, so what is it actually? Multi-label classification, for those of you who don't know, is a simple generalization of the standard classification process where you have, instead of one target, you have multiple targets. So a typical example are movie genres. A single movie might be a romantic comedy or a horror thriller with a sci-fi component, stuff like that. Medical codes are a typical example. Proteins have multiple functions. The interesting bit here is that the data is sparse in the sense that every single example we'll have only like 1 or 2 or 3 out of maybe 1,000 possible labels, but also for every label, generally we only get a few examples, so it's sparse in both dimensions. So what did we do? Our classifier chains are a really simple idea, similar to stacking if you want. We take one label arbitrarily, try to predict for that, and then we add the prediction to the data and predict for the next label and do that for all labels. So you can see an example for 4 labels there. Now, what do you do? How do you choose the order? Well, different orders give you a different performance. So this is a 6-label problem, 720 permutations, only listed 45 of them, different performances. The red bit is doing everything in isolation, every single label. That's the worst result. On the right-hand side, you average everything. You have an ensemble of those 45, not the 720, just the 45. You see the green is not the best solution, but it's a robust solution, and it's better than the red. So this was basically the idea. Have the chains and then use random ordering for the chains to get an ensemble that does really well on multi-label, on average. Of course, now this is where the opportunities come in. So instead of having a random order, people published very interesting papers being smarter about that, like explicit label hierarchies, label dependencies being exploited in a smarter way. Just looking at how good single classifiers are for single labels, because if you include the prediction, you want to be sure it's a good prediction. And then also maybe go away from simple lists to direct acyclic graphs, more complex structure. Then it turns a little bit into Bayesian network search, or at least you can steal ideas from there. So you have all these different orthogonal dimensions. I haven't mentioned some of them yet. The green bit is what you actually use as a base classifier. The main question is linear or not. The pinkish thing is this more complex structure. There's all kinds of ways to search and explore. And then also at prediction time, it's not straightforward anymore, especially if you have more than a chain. But even with chains, you can be more smart than what we have done. And so there's lots of different possibilities. But there's still, even though multi-label has been explored for a long time, and classifier chains have been explained for quite a while, a lot of opportunity, like unfilled areas. And one thing that I'm kind of passionate about is this interplay with neural networks, because we find that neural networks work really well for multi-label as well. But I think there's a niche there for a combination of neural networks and classifier chains in interesting ways. And I don't have much time to talk about that, but talk to me at lunch or later. And I should go to my last slide. And the time's up in 1 second. Thank you.